In this video, we're talking about how to find the first-order partial derivatives of a function, and in this particular problem, we've been asked to find the first-order partial derivatives of a function and then evaluate those partial derivatives at the point 2, 1. And the function we've been given is this function here, f of xy, so we have a function f in terms of two variables, x and y. It's going to be equal to x squared plus xy minus 3y squared plus 4. Now remember that when we were taking derivatives of single variable functions, we would be given functions just f of x, so this would be the function f in terms of just one variable x, and we'd have maybe something like 3x squared plus 2x. And so when we had to find the derivative of a function like this one, because there's only one variable, of course we're going to be taking the derivative with respect to that variable. In other words, we're going to be taking the derivative, treating x as the variable, and there's nothing really complicated about it. We just use power rule here, and the derivative of this, so f prime of x, which is what we would call the derivative, which means the derivative of the function f with respect to the variable x here, because x is the only variable, we'd get a derivative of 6x plus 2. So in one variable, it's pretty simple, but in two variables, when we have a function f in terms of two variables, x and y, how are we supposed to take the derivative? Do we take the derivative of the x and y at the same time, or do we somehow separate them? Well, the answer is when we take the derivative of a multivariable function, we have to take the derivative of each variable separately, and we call those partial derivatives. So because this function is in terms of two variables, x and y, we're going to take the partial derivative of f with respect to x, and then separately we're going to take the partial derivative of f with respect to y. If we had additional variables, for example the variable z, we could take the partial derivative of f with respect to the variable z. But in this case, there's two variables, so we're going to be taking two partial derivatives. And here's the notation for a partial derivative. Instead of something like this, f prime of x, what we usually write is the partial derivative of f with respect to the variable x. And this symbol right here is what we use to indicate that this is a partial derivative of the function f with respect to the variable x. So we have our first partial derivative. Now when we take partial derivatives, we treat all other variables as constants. So because we're going to be taking the partial derivative with respect to the variable x, we're treating x as the variable, everything else we'll treat as a constant. So in this case, we'll treat y as a constant. So let's go term by term here and find the first order partial derivative of f with respect to x. Well, if we look at our first term here, this is a polynomial function, so we can deal with each term individually. Let's look at our first term, x squared. The derivative of this with respect to x, well, there's no y variables involved, it's just x, so we would take the derivative of this with respect to x in the same way that we would as if we're dealing with a single variable function, because there's only one variable in this term, and it's the variable that we're taking the derivative with respect to. So the derivative of x squared is just 2x, so that's an easy one. But what about this term here? We have a positive xy, and we want to take the derivative with respect to x. Well, remember, we're just treating y as a constant, and sometimes what I like to do is think about y literally as a constant. So for example, let's pretend that y is equal to 2, right? 2 is a constant, and we're treating y as a constant, so let's just pretend for a second that y is equal to 2. If y were equal to 2, then this term would be x times 2, or 2x. We could think about it as 2x. Well, if we were going to take the derivative of this with respect to x, the derivative would just be 2, right? It would be the constant coefficient in front of our variable x. Well, remember we're using this 2 to represent y here, so by analogy we can say that the derivative of xy with respect to x is just y. And even if mentally we don't replace y with some constant like this value here 2, if we just think about x multiplied by y here, if y is a constant, then y is acting like a constant coefficient in front of this x variable here, and so the derivative of yx is just that y value there. What about the derivative of negative 3y squared with respect to x? Well, there's no x variable involved, so how do we deal with it? Well, in the same way here that we treated y as a constant to find the derivative of xy, here if we treat y as a constant, if we think about y being 2, for example, we would get 2 squared, which would be 4. 4 times a negative 3 would be a negative 12. This whole term would be a negative 12. Well, remember when we take the derivative of any constant, the derivative is always 0. So the derivative of this with respect to x is just going to be 0 because there's no x variable involved, and this is a constant. And in the same way, this positive 4 here, the derivative of that is going to be 0 because the derivative of any constant is always 0. So both of these terms go to 0 when we take the derivative because there's no x variable involved, which means that they're just constants, and the derivative of a constant is 0. So this this is, in fact, our first-order partial derivative of the function f with respect to x, and we can see that it's just equal to 2x plus y. Let's do the partial derivative of the function f with respect to the variable y and see what we get. So this time, we're treating y as the variable, we're taking the derivative with respect to y, and we're holding x as a constant. So that means that the derivative of x squared is going to be 0 because there's no y variable involved in this x squared term. We treat x as a constant. We have here a constant squared that's still going to be a constant, and the derivative of a constant is always 0. So this is going to be 0 when we take the derivative with respect to y. What about here, this positive xy, when we take the derivative with respect to y? Well, here again, x is a constant. It acts as a constant coefficient in front of this y variable here. So the derivative with respect to y is just going to be x. When we take the derivative of negative 3y squared, there's no x variables involved, so we don't have to worry about that confounding factor. We just take the derivative of this as we would if it were a single variable function, because there's only one variable involved, and it's the variable that we're finding the derivative for. So the derivative of negative 3y squared is just going to be negative 6y by the power rule, and then the derivative of 4 is just 0 because 4 is a constant. So these are our first order partial derivatives of the function, this one with respect to x and this one with respect to y. So that's how you find first order partial derivatives. In this particular problem, we've been asked to evaluate both of these at the point 2, 1. So we're interested in finding the value of the partial derivatives at the point 2, 1. And all we have to do there is plug in 2 for x and 1 for y to get the value. And the way that we write that notationally, we say the partial derivative of f with respect to x at the point 2, 1 is going to be equal to 2 times x, but we'll plug in 2, plus y, but we'll plug in 1. And what we're going to get is 4 plus 1, or 5. If we want to find the value of the partial derivative with respect to y at the point 2, 1, we say the partial derivative of f with respect to y at the point 2, 1 is going to be equal to, instead of x, we'll plug in 2, so we'll plug in 2, minus 6 times y, but instead of y, we'll plug in 1, and we'll get 2 minus 6, or a negative 4. And that's how you evaluate these partial derivatives at a particular point.